Good morning. It is Wednesday, October 30th, and it's time again for NASA Days, episode 4 this time. And this one's going to be a two-parter, so we'll do part 1 today and part 2 on Saturday. But this is going to cover the time between Challenger and Discovery, the dark times at NASA. So while the Rogers Commission was going on and investigating the Challenger accident, NASA independently performed reviews of all aspects of the Space Shuttle program. They also recovered much of the wreckage of Challenger from the bottom of the ocean. They recovered all 3 main engine controllers. They were severely damaged. However, NASA sent them back to Honeywell in Clearwater, Florida, where they were able to remove the 16K word non-volatile plated memory wiring, which was how the memory worked back then, and recovered a memory dump of the last frame from each of the 3 engines on Challenger, which is pretty amazing after sitting at the bottom of the ocean for a couple months. Multiple red lines had been violated as the engine was reacting to the loss of propellants coming into its feed system. 2 of the engines were in shutdown, trying to safe themselves. The third was voting for shutdown, but hadn't quite gotten into the shutdown phase yet when power was lost. Now, loss of power on a Space Shuttle main engine computer, the controller, will cause an engine to shut down because the electrical solenoid that applies hydraulic power to the valves will be de-energized, and the hydraulic pressure will vent out along the hydraulic drains, and the emergency shutdown solenoid, which is normally open, that we close at T-minus 4 minutes when we go to purge sequence 4, will go open due to loss of power, and it'll supply 750 psi helium pressure to the close piston of all of the valves, causing them to close, shutting down the engine. Now, how much of this actually happened, we don't know. As the orbiter was breaking apart due to aerodynamic forces and the engine and everything was falling out of the sky into the ocean below, we will never know how much of it actually got into the shutdown, where it ended up. But NASA also went and reviewed all of what they call OMRS, which stands for Orbiter Maintenance Requirement Specifications. It's the document that defines what testing you have to do and say everything is ready to launch. We also looked at all of the LCCs, or launch commit criteria, which governs when it is safe to launch. Within the engine project, the software requirements were reviewed and updated to make the system safer. I actually found myself at the Marshall Space Flight Center for a review of the main engine controller software. I had been studying the Space Shuttle main engine software, which was written in assembly language. However, they flowcharted it very nicely. It was very easy to follow how the software worked. I actually got in trouble for that. My boss didn't think I needed to dig that deeply into how things worked. He said that was NASA's job, and I worked at Lockheed, and our job was to process the space shuttle. So, to keep me out of trouble and to give me something to do during the downtime, they assigned me a task of developing a GOAL software program. Now, GOAL stands for Ground Operations Aerospace Language, and it was a software language that was developed at the Kennedy Space Center by the development team there, and it allowed non-programmers to define software and how it works in more English-like syntax. For example, you would have read some measurement and save as and give it a variable name. You would have verify a measurement is greater than a lower limit and less than an upper limit, then do something, or else. Or you'd have verify a measurement equals some value within X seconds, else do something. And so it was, written so that you didn't have to be a computer science expert to program it. Of course, my degree was in computer engineering. So my task was to develop a GOAL program that monitored all of the Space Shuttle main engine launch commit criteria. So I first created a display that gathered together all of the data for all of the parameters that went into the Space Shuttle main engine launch commit criteria. I think we had 25 30 launch commit criteria records for the Space Shuttle main engine. I grouped them into rows so you could easily compare the engines. We had engine 1 on the left, engine 2 in the center, and engine 3 in right, and you could compare across that. I also had them adjusted by function, so we'd have engine ready in one block, we'd have valve positions in another block, we'd have leak detectors in another block. Now, mission operations out at JSC, they organized their software a little differently. They organized it based on how the engines are located in the orbiter. So they had engine 2 on the left, engine 1 in the center because it's the center engine, and engine 3 on the right. That made sense for them because they communicated with the crew, and that's how the crew trained, and that's what they wanted to know, is the engines relative to where it was on the ship. It didn't really make sense for us on the ground. We were used to calling it 1, 2, 3, left to right, and that's how we had it set up. It was a minor difference, but it's just one of the examples of differences between JSC and KSC. So one of the measurements that we monitored for launch commit criteria was the fuel high pressure turbine temp before engine start. And if that temperature went low, it was indicative of hydrogen leaking past what they call the liftoff seal in the high pressure fuel pump, between the pump and the turbine area. And so we monitored that on the ground. I was actually at the Marshall Space Flight Center for that engine software review. And when I was there, they presented that they were rewriting the sensor processing section of the software. And by the way, I got to meet a lot of the software designers, the engine systems people, the people that test the software, because the Huntsville Simulation Lab, which was where they tested the main engine software, was right next to the avionics building. So they presented that they were redoing the software and for engine sensor processing, and they were going to iterate through. They had just created it all into a table, and they were going to iterate through all the sensors to make sure they were greater than the lower limit and less than the upper limit. And if that was true, then everything was good. If they were outside that bound, then they would post a report of failure. So I proposed, so the current limit for the high pressure fuel turbine temp was only used by the engine controller during engine run when it was starting to make sure that it didn't violate an upper limit. There was no low limit on the engine turbine temp. And so I suggested, hey, if you're putting it in a table anyway, you could replace the no low limit in the table with the actual launch commit criteria for that temperature sensor, and that way you could move that temperature sensor from being ground monitored to being flight monitored by the main engine controller for no cost. It's just a table entry. Now, initially, this didn't receive much support as I was expecting it to, because I was a Lockheed person. I wasn't NASA. I wasn't Rocketdyne, who makes the engines. And so I was at this meeting at the request of NASA, but I think most of the Rocketdyne people just saw me as somebody who was supposed to watch and observe and not really participate. So it didn't go very well, but a few minutes later, the manager of the engine systems group happened to be sitting in the back of the room for that meeting, spoke up, and he said he liked that idea of bringing it onto the engine computer. And that way it was in his sphere of influence more, and he had more control over that. And just like that, it was agreed upon, and we moved an engine LCC out of ground monitored into the flight control realm, in the flight realm. However, at the same time, they did add 2 additional launch commit criteria that were ground monitored, so I didn't get out of it scot-free, but they added 2 temperature sensors on the outside of what we call the anti-flood valve. Now, the anti-flood valve is a pressure-activated valve, so when pressure in the LOX feed system gets above a certain level at engine start, this valve will open and allow liquid oxygen to go into what is the heat exchanger. The heat exchanger is basically just some tubes that run on the inside of the high-pressure oxidizer turbine to warm up the liquid oxygen into a gas. And then that gas is funneled out of the engine, back up through the orbiter and into the external tank to use as a pressurant to pressurize the liquid oxygen in flight. So they were worried about leakage pre-start and getting cold liquid into the heat exchanger before engine start, before there was fire there, and maybe cause some brittle cracking and things like that in the heat exchanger, which if you have more liquid oxygen in the pre-burner, that's really bad, and you probably would blow up an engine. So it was very critical to monitor that. So they added 2 temperature sensors They actually bonded them, glued them right onto the outside of the pipe, downstream of the anti-flood valve, and we were going to ground monitor. They ran the wires into the orbiter instrumentation system to send to the ground so we could ground monitor them for launch commit criteria. They did some modeling and set the limits appropriately based on what they thought the temperature would get down to at that point in the pipe. So back at KSC, I returned to my task of developing this goal software to monitor LCCs. Now the computers at each console in the firing room were mod comps. I bet you've never heard of the mod comps, have you? They went out of business somewhere in the 80s, and NASA hired the remaining workers to sustain the computers in the firing room because we were the only one used them, and that was the last vendor that made them. So there's some contractual language usually in there that NASA can purchase the intellectual property if a company is going out of business. So those computers were 80s, vintage, 70s, 80s vintage. Each application, there could be 6 applications at a console. Each application could only use 1,280 words of memory for variables and 64K of interpretive code space. So it was a challenge to fit all of the measurements for all of the SSME, all of the Space Shuttle Main Engine constraints into that small memory space. But there were a few tricks that I learned from some seasoned pros, like you didn't need to store all of the data all the time. If we had a display and you could pick from channel A measurements versus channel B measurements, you only needed to store the measurements you were looking at. So that cut the number of measurements practically in half. That was a trick we could employ. And so that worked really well, and I was developing the software and it was coming along and we were starting to test it. As we were nearing completion of the testing phase, NASA kind of made a change to how they're going to do software. And they required all software development to be formed by a separate software development group. And so I transitioned and handed over my code and all the software to a amazing developer named Sherry, who was maintained, and I still maintain the responsibility for the requirements and verifying and validating the software when it was done, but she took over responsibility for the actually coding part of it. Verification is making sure that the software meets the requirements, where validation is making sure that the software performs its task that it was built for. Validation has to be performed by an operations person. Verification could be performed by a development organization. You're meeting requirements. That's usually where the development team gets paid, essentially, that you've met the requirements. We did an integrated V&V because I was an operations person and I performed the integrated V&V. We were able to do both verification and validation at the same time. So one of the final items to be completed on this LCC monitor, we had a lot of LCCs that were basically verify no major component failure on board. And a major component failure was deemed by the engine controller reporting a failure. And the way it did it was reported what they call a FID, or a failure ID, and a delimiter, and sometimes a parameter. So the FID and delimiter were octal numbers, okay? Because just how like humans have 10 fingers and we like to think in decimal, base 10, octal, I guess, is for people that don't think thumbs are fingers maybe, and they only use the rest of the fingers, and that's base 8? No, not really. Base 8 is because it's a derivative of multiple of base 2, which is binary. And if you have an 8-bit computer system, a lot of times you will use base 8 or octal. If you have 16-bit data bus, a lot of times you'll use hexadecimal or base 16. But there was a large number of failure IDs, and for each failure ID there was a large number of delimiters. And so how are we going to fit the decode of all of this possible combinations into this minimal memory space on the computers on the ground when we've already filled it up with all the display information? Well, the answer that Sherry developed was very clever, and it was to use a separate component program for the decode and to have all the text in a disk file. So you only had to read in the one record at a time when you were displaying the text, and that saved a lot of memory space. And the benefit of being a component program and having a disk file is we could share that and make that program available to others, like the engine console up at C3 at the front of the room, where we were in C12 at the avionics console in the back, and we could share the same component program, and so they'd have the same information we did. It was a clever solution. So with this software complete, we had to wait until September 1988 to see it used. And that is going to be Saturday's discussion as we get Discovery ready for its return to flight mission. And we'll talk to you Saturday. Have a great day.